I aired in a video a little while back here saying that every problem in this section could be done without a calculator. Forgot about these types. When you have an exponential equation with e, then you are going to need a calculator, more than likely, to solve it. But because we're going to turn this into a logarithm and a natural logarithm, we can calculate that on the calculator because we have a button for that. So let's see how that works. 217 e to the 0.024x equals 594. So let me give you just a quick interpretation of this, where this might come up. If you have a population that's currently 217, and that if it's growing continuously growing at a rate of about 2.4% per year, per week, per day, whatever the time frame is, the growth rate is about 2.4%. Then how long would it take for that population to grow to a total of 594? So that's actually an interpretation of this problem that would be valid. All right, well, I want to isolate x, and first of all I'm going to divide both sides by the 217. So I have e to the 0.024x is 594 over 217, and that's going to be an ugly decimal number. I don't even want to think about it yet. We'll just punch all that in at the end of the problem. Because a mistake a lot of students will make, they'll punch this in their calculator because they don't want to write fractions. So let's see, 594 divided by 217 is 2.73732718894. Well, how many decimals do you write? And if you round this off and say, well, it's 2.7, then you've cut it off so short that you've just made a pretty big error. And sometimes those errors can really balloon in these kinds of problems. So it is safest to not even touch the calculator until you're done, until you're ready to get the final answer. Then you can round the answer off. So, because the principle is if you round off decimals early in a problem when you're calculating, and you calculate with rounded off decimals, then you're going to compound some errors and make some big mistakes. Sometimes, most of the time, actually. All right, so here I have e to a number equals to this number. All right. Well, let's just think about how that works. The e is the inverse function of the natural logarithm, and so the natural logarithm of the right side, 594 over 217, equals to the exponent, 0.024x. All right, so that may not be immediately clear to you, but if I didn't use the ln notation, if I use log base e of 594 over 217, that would equal to the exponent, 0.024x. And so, e to this power equals that number. It's simply the logarithm form, except we don't write log base e, we write ln for natural log. So that's all there is to that, actually. All right, and well, to finish, I'm going to need to divide both sides by this coefficient, 0.024. So x would equal to the natural log of 594 over 217 divided by my coefficient, 0.024. So now we've solved for x. Let's punch the numbers in. So I'm going to enter ln, parentheses, left parentheses, 594 divided by 217, close in parentheses, and then divide by 0.024, and we get 41.96 approximately. So x is approximately 41.96. Okay, there we go. So how far do you round it? That really depends upon the need of your problem and what kind of accuracy you need there. But because I didn't round off anything before this point, this answer in my calculator is the most accurate answer we could produce. And then we'll just round it off. So, okay, time to do another one. Here's another exponential equation. Solve 245 parentheses 1 minus e to the negative 0.36t equals 180. So it turns out this kind of equation could be used as a learning curve for the spread of rumors or the effectiveness of an advertisement. How many people have seen an advertisement? It's a function which, let me just sketch the graph of it so you kind of get a sense of what it looks like. It's, what would it be? It would literally look like this. It's an exponential function, and it would go down this way, incidentally. But we're only interested in time being positive if it's a real application, and this means time. Then really the function is going to start at the origin, not at anywhere else. So the horizontal asymptote would be, now I'm talking about this function here, y equals to 245, 1 minus e to the power. The asymptote would be 245. So a function, f of t equals to this, would graph this way. It's asymptotic at 245, which means that in time it's going to approach 245. And somewhere around here is 180. And so what we're solving for is this t value that gives us 180 along this curve. So that's kind of a picture view of what we're doing. All right, so let's look at the mechanics of solving this problem. And it's kind of like the last problem, except it's slightly more complicated. All right, we want to isolate, in this case, t. So first thing I'm going to do is divide by 245. So divide both sides by 245. Then we have 1 minus e to the negative 0.36t equals to 180 over 245. And it's up to you if you want to reduce that fraction. Let me see, if I divide both sides by, top and bottom by 5, we'd get, let's see, 36 over 29? No, or that's not 29, it's 49. All right, 36 over 49. This is optional. Okay. You don't have to, we really don't have to reduce this fraction because ultimately we're going to plug this all into a calculator, but I like to reduce my fractions most of the time, or when it's fairly easy. All right, now I'm going to subtract 1 from both sides, and so negative e to the negative 0.36t is this fraction 36 over 49 minus 1. All right, and you can leave it like this if you want and ultimately plug everything into a calculator. But because I'm me, and this is a pretty easy one, 36 over 49 minus 49 over 49 would be what? Negative 13/49. Okay, so just subtract 1 from that fraction, you get this negative answer. So I have a negative e something equals to negative, and multiplying both sides by a negative 1 would cancel the negatives. And I'll have to because I can't have an exponential function by itself equal to a negative number. But it doesn't in this case. The negatives cancel. All right, now let's convert this equation into logarithmic form, and we'll use the natural log. So the natural log of the right side there, 13/49, is equal to the exponent, negative 0.36t. So time, t, will be this logarithm, natural log, 13/49, divided by the coefficient, negative 0.36. So divide both sides by the negative 0.36. And there we have it. Let's punch that in the calculator. And by the way, it's going to be a positive answer because the logarithm of any number less than 1 is going to be negative, provided the base of your logarithm is a number greater than 1. All right, so natural log parentheses 13 divided by 49 close parentheses divided by negative 0.36 is 3.69. So 3.69, it rounds up to. It's 3.6857 something. So I hope you're running this on your calculator with me to make sure you can get these numbers. All right, so I'm kind of out of board space here, but I'll write it over here. T is approximately 3.69. There we go. So we're done with that one. And you could check this by literally plugging that number in. And now if you just type in 3.69 and put it here, the left side is going to be close to 180. It won't exactly equal 180 because if you just plug this number in, it's been rounded off, you've created an error. So the left side is not going to quite equal 180. It should be pretty close. I mean, within a tiny fraction. If you use all the decimals in your calculator, then it's going to either equal 180 when you plug it in, or very, very, very close to it. So anyway, there we go. So solving those problems, and these applications are realistic. You do find equations like that in real applications with e's in them of this nature. So solving those is a matter of pulling out the calculator and using the natural log button once you've isolated the variable. So, okay, well, that does it for this topic.